editors or ID, right? So that is the system software for building applications. I come back to a diagram that show you a typical building application building process for a so you see that from this diagram you see that we have generally you have two phases, right? The compilations and the linking, right? The compilation, that means we translate from a source program into something called object programs, which is represent the series of instructions in underlying architectures, but it's not, but it's incomplete. This is separated to each other of the object programs, and the linking process, that means we combine the objects code together and make the executables. So this is the general building applications process using the separate compilation, right? And the other kind of system software is to manage the executions of the user application. And you know that most of the today the applications run under our operating system, and the operating system will play a role for manage the executions of our programs. Yeah. Sorry, somebody talking? Okay. So the for the management of executions of user applications, we have operating system play a very important role there, and of course the operating system consists of a lot of subcomponents inside. Is the for example, you have loaders, you have some device drivers. There are some interface to the application. We call that the system called etc. Okay, I will explain to you more details in the next part. So this is the this diagram show you the general process and the structures of the operating system. Okay, for explaining more details about the different kinds of entities relating to the two process. Last week I explained to you the what is the source programs, and you see that I will recall some information from that. For example, in that source program, the most important thing is that source program may be separated into several several parts, 7 units, right? And in a single unit, you may have some reference to the entities of the other units or libraries. For example, in this very simple example here, you see that we have instructions or the statement like printf hello world. So this is the invocations of the function printf in the library, right? But the problem is that the function printf is not defined inside that source programs, and similarly in many many other source programs, we have some reference which is not defined inside that source programs, right? Here is the definition, exact definition for the printf is realized in the a library, a standard library of C, which is called libc in GNU GCC. And of course, we might call a functions which is defined in another source programs, but obviously when we try to compile that source program into an object file, so we will obtain some object code. The object code which is okay. Maybe I will try to demonstrate to you some a little bit demonstrations to you. Okay, let's see that we have a simple source program, say test.c. Okay. Something like this. Let us show that this is this is the simple source programs, which is called the two functions. The first function is printf, and second function is add. The printf is defined in the library, and add is defined in another module called the a.c. Right? Something like this. Then we can call this compile the test.c by using my gc-c test.c. So we will obtain the object code like test.o. What is inside test.o? Actually, test.o mainly consists of a series of instructions in the underlying machines. For example, in my case here, the underlying machine use the x86 64 bits. So we can try to use some tools for examining the instruction inside that that object code. For example, let me remember that object dump. Here we have some tools like object dump. That means that it can display the information inside the object file. So there are several options for using the object file, but there are very special options which is allow you to disassemble for the object code. So what is the disassembly? They translate from the binary to the assembly language. That's all. So for example, I use obj dump minus g for the object file at s.o. So we will see that the series of instructions which is written for the object file. So here we have two call. The first call is to the maybe to the function add, and the second call to the function printf. So this is the instruction, but you might realize that the address here is not correct. So we're missing the actual address of the function add and the actual function of the function printf, right? So that is the very important properties of the object call. There are some reference, some address is missing in the code. Okay. Some address referring to code or data might be lack due to the separate compilations. Similarly, we have here the compilations in the slides. Actually, in the slides, I use the 32 bits compiler. GCC for 30-bit system, 32-bit system. So it is a little bit different from what we have just seen from the demonstration. But in general, we don't we miss some address here, and we also have at the time of linking, when we combine several objects code and a library also, and several special object files, we link them together, so they will try to calculate the exact address for the entity we refer. So at this linking times, the actual address of that we're missing in the object file will be fulfilled. So after that, we will obtain a complete executables without any missing reference. So if we have an executable, so that means we don't have any missing reference there. So we will we can load that executable into memory and then execute the code from that memory. Okay, so that is the important properties of the object file I already explained to you in the last week. And the next entities in the flow of the user application creation is library. Library actually library is some existing subprograms, subroutines, maybe function or procedures, or sometimes in object-oriented approach, we have the existing class. we are already implement this and want to use this in the other programs, then and of course it can reuse in many applications. So we will pack these functions or procedures, or we call some subroutines in something called the library. Actually, library is we can consider library as an object, as an object file. Actually, library is the combination of several object files into a some archive format. So from this by packing the object file, the implementations of object file, so we can have some precompiled code to be reused in many applications. Of course, in order to use that library, you need to have some standard or some agreements about how to use that library. For example, the standard library in C, we have libc. Libc consists of many functions like a printf or scanf or malloc or something like this inside that library. And when we try to link programs object files and make an executable, you should link it with library 2. Of course, you see that I do not have to specify the library in the command line. When I try to do some gcc -o test test.o, when I try to link that test.o here, I don't have to specify the linking the library, the standard library here. I mean libc. I do not have to specify this here because this is a standard, and this will automatically added into a list of object file to be linked. But if you have some special library, you might have to specify the library by some options to the linkers. For example, if you use GCC, you might have to specify the option like L, right? For example, if you want to put some math library, a mathematical library, you may have to put for example, math, or you might have to put a library like ABC. Actually, if you try to link with the L.abc, so that means this will be linked to some special library called libabc. They will try to find some libabc in for example in you see that there are many you see that there are many library here. So if you want to use the standard library is stand for the libc here, and if you want to use math, so you need to have some libm here, and if you want to use ABC, so you need to have something like a lib ABC deployed into that that path. Okay, so but as far as you see that there are actually two types of libraries, the static linking library and dynamic linking library. Is anybody can distinguish that two kinds of library, static linking library and dynamic linking library? What is a static linking library and what is the dynamic linking library? Guys, anybody here can help me to distinguish the two kinds of library, static linking library and dynamic linking library?
Sir, may I have a take at this?
Please.
I think that the static linking library is built in the code, while the dynamic linking library is saved it stay on a separate file.
Yes. Actually, the term statics and dynamic refer to the things that we have some properties which is not granted in before the execution. So that is the statics, and for the dynamics, that means that property should be granted during the execution. So that, for example, if you want to use some function f, so f can be linked before the execution. So that means the static linking. But you also right in this sense. So normally a static linking library are considered like in the most of Object 5, when you link a program to a static linking library. So actually we will try to join the core of that program and the core of the library together and to make a bigger one, to make the combined core of both program and link library, and then they will resolve the reference from the core of program to the functions in or the data in the library, right? So that is the combinations of the core. So for the dynamic linking library, you also write in the sense that the library are implemented in a separate file. For example, we have in Windows we have DLL, right? DLL actually stands for the dynamic linking library. So at the runtimes, we are trying to load DLLs into the memory, and when we capture the address of a function defined in the library at runtimes and call the function. So in this case, the functions, the address of the function in dynamic library we do not know before the execution. So in this is the case of dynamic library, dynamic linking library. Of course, the dynamic linking library, because we have we develop the dynamic linking library in a separate core, so on a separate object file, and we do not have to combine this library together with the executable. So the executables can be smaller, and likely the library can be reused in many applications. So that is the concept of linking, static linking and dynamic linking. Actually, we have the another kind of libraries which call shared objects. So do you see this in this? The extensions for the library here is .so, right? You see that this named .so. This actually stands for shared objects. Shared objects is another kind of library. And we can consider the shared objects as a kind of static linking, because the the reference to the functions of the shared object should be should know before the execution. So but actually the but okay, what is the shared objects? And what different from a shared objects and the traditional static linking library? You know that if you have a static linking library, whenever we want to make a programs, you need to combine the code of that piece of program together with the code from the library together, right? For example, if you want to static linking with libc, so we need to join the libc inside the core of your programs. So the problem is that there are many applications inside your system. So whenever you do static linking, you will copy an instance of the library code inside your programs. So this will this will cost you. For example, your program become bigger. Every program become bigger due to the instance of the static linking library, right? Especially for the case of the standard library like the libc. if you totally do static linking for libc, so for any application you might have a libc there. So the problem is that you have a bigger file system to store the executable in this case. But actually, the file system is not the big problem. The big problem is that whenever you load a program into the memory, you need to load the whole execution code on into the memory. So so if you do static linking, so there are many instances of that libc in memory. You might have hundreds the process, 100 programs running simultaneously in your system. So if you use the static linking strategies, so in this case maybe there are hundreds instance of libc exist in the memory. That's not good. So share objects in this case help you to share the code of the library to every programs that want to use it. So if you use share object, that means in the memory you will have only a single instance of the share objects. And then when you do link, actually we the address to the library is not yet known, but at the run times when you try to load that programs, so we know the exact functions or data from share objects in the memories. So in this case we will fulfill the missing address. So that in that approach, or some some other approach for this is that we can fix the address of the functions in some appropriate locations in a virtual system, memory system, and after that we can map that share objects into the designed positions in the memory space of the application. So this is the other approach we can use with a share object. For the second approach, we can at the linking times we know the address of the functions we want from the library. Okay, that is some explanation for you in about the libraries. Actually, this is much more complicated in the case of dynamic linking and the case of share objects. But I will stop here and try to explain to you later in the part object code. Okay, the executable code is actually the code from the programs and code from the static linking library and code for some special objects. And the executable code is we can load this into the memory using some loaders, some special loader. Okay, compiler. You may know that you already know that the compiler is the computer program is try to translate from source program into the target programs. For example, into the object code. So I try to recall some informations related to a compilers. So you know that a compiler has two big phase, the front end and the back end. Front end is actually trying to do something like lexical analysis, right? And then syntax analysis, and then tries to semantics analysis, right? So this is the roles of front ends. So at the end, front end might generate code in some special form we call the immediate language. And if you have some errors in your programs, for example, lexical errors or syntax errors or semantics errors, so all of the errors will be discovered at in front end. And from that, the second part of compilers is backend. Backend actually they will try to optimize the intermediate language to have a better versions of the immediate code. And finally, they will translate that immediate code into a target code. So at the end of the backend, we have a target code. So the role of backend mostly for the optimization. We need to do optimize the immediate code to the better version. Do you have learned the compiler construction and compiler construction lab? You already studied the compiler constructions?
Yes, we did.
Okay. So actually, in I also the persons who define the syllabus for the course compiler construction and the compiler construction experimentation lab. And I know that in the experimentation lab, we have a very simple approach for making compiler. We use the approach of top-down compiler and with the one-pass compiler, right? Okay, maybe I have to tell you that because my specialties is about the compiler construction. So actually, at the beginning, I am the person who designed this course, but unlucky that I I do not teach that course because this course is assigned into the computer science department. Computer science, yes, computer science department. So the lecturers from the computer science department will teach that course. Okay. Come back to the point here. Most of model compiler do not design like the one used implement in the compilation lab. How they really implement a compiler. So actually, we have several immediate code, existing immediate code, and from that existing immediate code to the end, that means the backend is already exists. For example, Java bytecode is kind of immediate code for the translating from the source program into the immediate. Java bytecode is kind of immediate code. We have another thing, UL, immediate language. It's just the kind of immediate code for the .NET frameworks. So most of the .NET language, like Visual Basic .NET, C#, or F#, something like this, they will compile into the same immediate language like IL from the then from the IL to the target code or to something special, we can have some backend compiler to do this to you. In open source communities, there's a very famous backend. I can tell you, it's RVM. This is a very famous backend. You can try to Google it. RVM. This is we have some existing backend RVM. That means they are already defined to use the immediate language, implement to you the optimization phases on that immediate language and generate the object code to you. So this RVM do, and the remaining things for developing a new language, in this case, it just implement the front end, including the lexical analysis, syntax analysis, and semantics analysis. And even that in the front end, you also have some tools for it, like you have some Lex or Yarks, Flex or Bison, or some special tools like an error. That will help you to define the the front end, the parser or scanner in the front end. So that means actually today the task for making a compiler is not so complicated as before. We already have to define the lexical structures and syntactic structures of the language in some very special form, like lex or yards and or else, and then try to map that syntax trees into some immediate language. That's all. This is the task for definitions, task from front end and back end of the compiler. Okay. Since we compiler is a very important system programs we have to study, but because you have a separate lessons, separate lectures on compiler, so I do not have to repeat this in this course. Okay. Next, assemblers. What is assembler? Assembler is a kind of translators from the assembly code into binary code, right? So normally we for example, when you have a programs, high level programs like this, you can try to when you compile test.c using the minus s like this, so you will obtain some assembly code for the programs. So here is the assembly code for the programs test.c. So program unit test.c. Of course, you can try to modify the instructions here if you want, and then using the assembler for translating this code into the object code. Finally, we can use the you can compile that code using some assembly. Actually, here I use the GCC for the compilations of assembly code. GCC is an assembler, but actually GCC is just a script. They will try to call several programs according to the arguments here. For example, if arguments here is an assembly code, so it will call the assembler. The actual assembler for Linux, I think this is okay. I just forgot the the standard new assembler, maybe this is I think this is AS. The AS, the commands for that GNU assembler in Linux is AS. AS. We have this is the of course there are many options for using AS, but I'm not sure how to use this because I've never used the AS before. Okay, let me try to use with the standard AS -o test .o test dot s. Okay, it was so it generates the object file from the assembly code test.s. So actually, AS is the GCC minus S minus O for test.s is just abbreviation, shorthand command for AS. Okay. About the assemblers, you know that the every architectures, microprocessor architectures, we have the assembly language. So assembler is transformed from the program in assembly language into the object code. So actually, that that kind of translation is not so difficult because that translation is the type one-to-one, one command to one binary instructions. So that is not difficult to do the assembler. Okay. Linkers is more much more complicated. They try to combine several object files into an executable into single object table. So they have to arrange the contents of the object file into an appropriate order, and try to design the loading location for each part of the program into the memory in the future. And of course, there are many missing address in the object file. So linkers should fulfill all the holes that appear in the object file when you combine. So you need to retargeting, absolute jumps, load store, try to filling the call address for the call instruction, etc. So that is the role linkers. We will have different course, different lectures for linkers. Okay, the next one is operating system. The biggest guy here. Operating system is a set of programs that manage the computer hardware resource and provide common service for the application software. Okay. Like I said before, inner multiple user uh, 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 multiple program multiple process running simultaneously in a system. We have some common resource for all the programs, like a screen, like keyboard, like other peripherals, or we have a common resource like memory, like hard disk, right? So accessing to the common resource is very very important. The the user program cannot be directly accessed to the common resource, because if you directly access to common resource, so in this case there might be conflict with the other process. So because that we need to have some mediators that help you to resolve every conflict of the sharing resource. So operating system is just kind of that kind of mediators for you. Actually, they will make this by providing some service to the user application, we have some kind of program execution service in the form of system call. So whenever you want to use some resource, you ask the operating system by invoking the system call, and you will get what you expected from the operating system. This is a program execution service. And one more important features for operating system is they provide the user interface, user service. For example, the Windows system, the etc. Okay, that is operating system. We will go deeper inside the operating system, especially for the same part like a file system or device drivers. System call. As I just told you that whenever you you want to access to some device, or you want to access to some common structures or common resource of the system, so you need to ask the operating system to do this. But how operating system receive the request? They will have to make that request in a very special special way. Wait me a few minutes. Okay, sorry. So normally you request some service. In your programs you request service from the operating system, like the request is normally divided to several parts, like request to process control, for file management, for device management, etc. Here is some thing you need to to ask operating system to. So in this case, the operating system will make some interface for the service like this, and that interface is not like the interface of the function call, but this is we have a very special interface using some sub interrupt instead of function call. Why we don't make that system interface as a function call? Like this. Here is, for example, here is you have the user programs, and if you want to consume a service from the operating system, you will have to invoke a system call by calling the emit the instruction int sub interrupt int. Why we need to use? Why we do not have just simply using call to the function that implement the service? Why we have to make something very complicated here? The reasons is that as I told you before, we have some restrictions in user mode. There are several instructions we need to limit to the user application. For example, in out, we don't as I remember the previous lessons I told you about the foreign execution, right? User mode application running in ring 0, and in the operating system run in a ring 3. So when we move from the user application to the operating system, we need to change this execution level. So in this case, the normal call instruction do not help you to change the execution level, but the sub interrupt here will help you to do this. This will help you to change the execution level, and whenever you finish the service, it will return from the operating system to the user applications using the direct return from interrupt. So this will move from the current mode to the user mode. That I means the execution level. So this is the reason why we call a service to the operating system. We have to use the interrupt, soft interrupt here. And okay, so the system call cover all the service of the from the user application to the operating system. Of course, that many, but they always try to minimize that setup system call. So, for example, we have the same system call to manipulate with the peripheral, with the device. We use the same system call for a device with the system call for accessing to file. So this is the case of Linux. Linux considers a device as a file. So in order to use the device, you also have to open, you have also to read, write, or control. Similarly to the normal file. So actually, by this way, we don't have to extend the system call when you have a new device. We can use the existing system call for device. For example, in this case, is the system call for file management. Okay. The next part is about device drivers. The device drivers is actually a part of operating system, but it's not. It's normally not developed by the operating system developers. But this is developed by the kind of third-party organization. So, for example, when you design a new device, in order to control your device, you will have to make device drivers so that you can plug your device to a computer and use that device driver to control your device. But device driver should have some standard to be implemented. Normally, we have some redirection from the system call to the function implemented in the device drivers. For example, if you want to use a device, you normally in high-level language use the function open and give the path of your device file. So actually, when this these functions open is called, and then the corresponding system call will be invoked. The open is system call, and that system call will redirect. We will redirect to the actual implementation in the open functions in device drivers. So in this case, we when we implement a device driver, that means if the operating system offer any service to the device, so you have to implement the same service in your device driver. And of course, it's not simply like this. Sometimes we also have to deal with the problems of concurrency. That means if you have more than one application or more than one process using the same device, you will have to control that concurrency. So this is have to be implemented in the device drivers. Or another situation is that the device driver might the response device driver might be not immediately. Maybe you, for example, when you read something from hard disk, you cannot read this immediately, just like in the memory. You need to wait for some times for the hard disk to read it. And of course, you cannot wait. You cannot stop the processing and wait for the hard disk to return the value. No, this is just waste of times. Actually, you have to make some kind of interrupt. For example, you ask hard disk to return some block in the hard disk, and then you come back to the other tasks of your programs or tasks for the next process in your program, in your system. You do not have to stop there and wait for return value. No, you just need to put some interrupt there, and whenever the data is ready to feed to the CPU, so the device will raise a hardware interrupt. So in this case, we will come back to the system call process and try to resume the the execution after getting the contents from the. So in this case, the device driver should be collaborate with the schedulers of the operating system to make this happen. Okay, I will show you more details in the lessons of device drivers. Okay, device drivers in Linux. A device driver is provide service supporting the communication with device. We have basically we have three kinds of device drivers. The character device drivers. That means we have some streams of device can be considered as a stream of the data. So we can read this byte after byte, and we also have a second another kind of device driver like block device drivers, which is normally implemented for the device like hard disk, like optical disk, like flash USB, etc. And the last kind of device driver is network device drivers, which is implement the network stack. Now there are several other system system programs. For example, this might not so important, so I might not introduce this to you in the rest of the course, but I should mention them here. For example, an achiever. Archiver actually just a program to try to create an archive file for some programs of some data. For example, tar is an archiver. Tar just they can group several files together and make one archive file. During that process, we can make some compressions or some encoding. So why I say that archivers is a system call because it's related to the techniques of making library. Actually, library is just an archiver, archive file from several object file. So making we have some utility functions to make the library. Actually, they use the an archiver to do this. The maybe the common use the archivers in Linux system is tar or but the standard one is R. R here is actually the archiver which is can be used for making archive and especially making library. Okay. So that is the rest of the lessons for today. We also finished the first part of introductions. So next time we will go to the second part of programs. Okay, we finished today lessons. See you next week.
Thank you, teacher.